Welcome to the fourth chapter on safety and contracts in the Logical Foundations of Cyber-Physical Systems textbook. Or we'll now look into a lightweight introduction into safety specification techniques for CPSs. Why? Well, because CPSs are subtle. We don't want to just build them. We want to make sure we build them safely. Last time, we've seen hybrid programs as the programming language for cyber-physical systems, with the most unique features being, on the one hand, non-determinism, so the fact that we can describe models with different sets of possible behaviors, which was very important, for one thing, to describe the uncertainties of the world around us, which certainly we are uncertain about, but also to describe deliberate simplifications of the set of possible behaviors our own controllers could do, just in order to make the description easier. Real numbers were important in hybrid programs, to describe real positions and velocities, for example. But the most important defining characteristic was the occurrence of differential equations right in the middle of the program, and that gives hybrid programs a way of describing fancy mixed discrete dynamical systems and continuous dynamical systems, thus hybrid dynamical systems behavior. But of course, it's not just a matter of developing a very powerful language for describing the behavior of processes that evolve in complicated ways, because we also need to make sure that all of those behaviors are safe, and that's where the contracts come in. You may have already experienced the use of contracts in ordinary discrete programming languages, and you may have seen that even if you just use them for dynamically checking in test cases whether everything is working all right, that they help a lot. Because contrast this with the use of manual debugging techniques. In that case, you'll have to work backwards from a symptom that a program isn't behaving, which you have to find out by manually observing it, and then from that symptom debug your way backwards to the actual root cause, which can be very different at a location. But in contracts, when they're used for dynamic checking purposes, the first contract that fails is much closer to the line where the problem is. Now, dynamically checking contracts isn't good enough for cyber-physical systems. And why is that? Well, suppose you're flying an aircraft with a fancy autopilot that's been developed with contracts all over the place that are, however, only used for dynamically checking them. In that case, one of the contracts could be that the aircraft should never be pointing strict nose down when it's just 100 feet above ground. It's a sensible contract. But suppose this contract fails a dynamical check. Well, then what do? It's already too late. You're already pointing nose down when you're 100 feet above ground, which will probably make you curse the developer of the software for only now telling you when there's no longer a chance to change the design of the system. In other words, because cyber-physical systems have so much impact in the real world, we need to make sure right from the get-go that they're going to be safe, not just in the occasions we test it, but always. In particular, even when we're testing them, due to the phenomenon of non-determinism, it can very well happen that one non-deterministic behavior of the exact same test case is good when another one is bad. And we really want to make sure all possible executions that a cyber-physical system can have are good. This is what leads us to the study of contracts. On the modeling and control side, we will look at the role that discrete and continuous dynamics play in contracts and in analytic specifications. On the computational thinking side, we will use rigorous mathematical specifications of programs using contracts with both preconditions and postconditions. Preconditions express the expectations we have on the world around us in the initial condition before it's safe to turn the CPS on. Postconditions express what the CPSs guarantee after you're using them. We will look into the most fundamental concept for the entire textbook, differential dynamic logic, which provides a logical way of capturing behavioral properties of hybrid systems. We will be using differential dynamic logic fundamentally in this course, in this chapter, for specification purposes of hybrid programs, but right next time around also for rigorous reasoning principles for hybrid programs. On the CPS skills side, we will look into more detailed elaboration of the model semantics, especially as they relate to safety properties and contracts, but also will begin to plant the seed for reasoning principles for CPSs. But first, let's develop a running example. Now, we will look at quantum, the acrophobic bouncing ball. Admittedly, bouncing balls are not the most amazing CPSs. In fact, they're totally impoverished CPSs because the bouncing ball didn't even bring his computer along. But the point of this simple example is that it still exhibits exactly the same kind of interesting hybrid systems dynamics, and it's easier for us to understand. Besides, you don't have to immediately run off and buy a self-driving car kit just to follow along with what I'm saying, but just go ahead and grab yourself a bouncing ball. Because you've probably never seen one before, I brought one here with me. Here is a bouncing ball that's falling in gravity and then hits the solid earth and is bouncing back up and then bouncing back up and bouncing back up and bouncing. What's the model of that? Well, certainly, while the bouncing ball is falling, gravity is acting on it. That means it's subject to the differential equation, where the time derivative of the position equals the velocity, while the time derivative of the velocity is minus g for gravity. Gravity is acting on it. But that alone would not be a very useful description of a bouncing ball because it's supposed to bounce above ground. It's not supposed to fall through the cracks in the ground like in this example here or there. And that's, of course, easy to fix. We just add an evolution domain constraint that says we're following this differential equation, but only while we're above ground. Now, when we're on the ground, something has to happen right here. And we could go off and read a physics textbook to understand the role that elastic deformation and plastic deformation play on the ground, and then the slow compression with the elastic deformation is being undone, leading to a decompression phase when the ball will begin to convert the accumulated energy back into motion energy. That would all be fabulously interesting physics, but it also is a very complicated model. Instead, it's much easier for our purposes if we exploit the hybrid systems principles, where we combine different phenomena with one another in a compositional fashion. We say that the continuous falling of the ball through the air, that's the typical continuous dynamical systems motion, but the sudden change on the ground, where the direction changes suddenly, that's more naturally understood as a discrete dynamical systems transition. So let's develop that. Basically what happens is, not because of computer control, but because of physics control, the phenomenon that if the ball is on the ground, then it inverts its velocity, which used to be pointing downwards, to the negative value of that, so that it is pointing back upwards, although with a certain damping coefficient C applied. And now, after following this differential equation, the discrete control is running. Well, that describes the motion of the bouncing ball all the way up till here, and then the model doesn't go any further, which means we need a repetition in the model to say that, yeah, the sequence of continuous dynamics and discrete dynamics and continuous dynamics and discrete dynamics keeps on being repeated over and over and over, possibly. Notice, this, for example, describes how we're following the differential equation of the bouncing ball all the way up till the ground, where x greater or equal 0 is still barely true, x equals 0 is still true. And then we stop the differential equation at that latest moment in time, follow the sequential composition, to run the discrete control, which says, yep, we're on the ground, so let's change the velocity from negative to positive, and then we keep on following the differential equation again. But gravity is still acting on it, so at some point gravity is going to win over and send the ball back down. Notice here, for example, we could stop the differential equation at that point already. That's legitimate. The duration of evolution of a continuous differential equation is non-deterministic. We're still inside the evolution domain constraint. If that happens, then we stop, follow the discrete control, which actually doesn't have any effect at all because we're not on the ground. No harm done. We repeat the control, for example, follow the exact same differential equation again from the exact same point and just keep on falling. But at the latest on the ground, do we have to stop the ODE because its evolution domain constraint would otherwise become false? And so the discrete control again makes it bounce back up and bounce back up and bounce back up. Well, that's the hybrid systems model of the bouncing ball. It's much easier than any physically precise model. Notice, if we put our hybrid systems glasses on, all of a sudden we discover interesting dynamics is happening in the middle of this picture here, because at this point in space down there, there's actually a discrete change. So we discover a crack in the fabric of time where at the next point in time, the next instance of time, which is happening at the exact same real duration, does the velocity suddenly change backwards from a negative value to a positive value, and then we follow the flying differential equation where gravity is still acting, so we come back down, we jump on the ground to a positive velocity again, and then follow with a positive velocity until gravity is winning over and makes it negative again. Make a jump and follow and jump and fly and jump and fly and jump and fly and jump and fly and so on. In fact, when we look at what time does in this funny evolution, is that hybrid systems, time evolves continuously for some time, then jumps continuously for some time, then jumps to a next time step, continues next time step, continues next time step. So if I plot just the bottom of this picture separately, we discover that time actually is a two-dimensional quantity of continuous time and time steps going up. Well, this is a useful way of gaining an intuition for what hybrid systems do. Notice the specific time domain is very specific to the particular motion that the bouncing ball did do. And that means it would be very unhelpful for our purposes if that's how we were to define as actual semantics. It's much easier to go compositionally, which is what programming languages are good at, and say, well, there's a continuous dynamics process of falling, there's the discrete process of switching, and the two of them are merely being put together by program operators, such as, for example, the sequential composition operator, or for that matter, the choice and test operators that are really underlying the if condition here. Let's also understand that the bouncing ball model is still a bit funny, because the bouncing ball keeps on bouncing and bouncing and bouncing and bouncing, and if you try that out in reality with your bouncing ball, you may find a bit of a discrepancy there. You can try it again, but ultimately it will actually lie down flat on the ground. Of course, again, you can take more physics courses and understand how exactly at what moment the remaining energy that it has after subtracting the friction essentially that happened on the ground isn't enough anymore such that the elastic deformation kicks the ball back in the air. But it's much easier to still keep on exploiting our hybrid systems principles, to say, well, when we're on the ground, there's two possibilities. The one is, as before, that we bounce back up. The other one is to non-deterministically instead choose the velocity to become zero from now on. Just as in this evolution. We fall, and non-deterministically decide to bounce, fall, non-deterministically decide to bounce, fall, bounce, fall, non-deterministically decide to remain flat all the time. Basically, this is how a bouncing ball is becoming deflated. And it is, of course, much easier to write down this phenomenological description of the model. The behavior of this model includes the real behavior you see in your bouncing ball. It also includes other funny behaviors, such as keep on bouncing all the time. But if we succeed with a safety analysis for this easier model, which includes the real behavior, then we've done so in an easier way, which is good for us. So let's go back, however, to the original model without deflating, just for the sake of argument, to make our analysis a bit easier later on. Now, the next question we should worry about is the question what a safety for cyber-physical systems really means. And at that moment, you'll probably think bouncing balls are boring, so let's talk about real robots here. When is a robot safe? That's a tough question. Fortunately, Isaac Asimov already argued how to do that with his 3 laws of robotics. First, a robot may not injure a human being or, through inaction, allow a human being to come to harm. Makes sense. Second, a robot must obey the orders given to it by human beings, except where such orders would conflict with the first law. Makes sense. Third, a robot must protect its own existence as long as such protection does not conflict with either the first or the second law. Beautiful. I guess now we know what safety of robots has to look like. Well, except if you're trying to render these 3 laws of robotics with the precision in logic, you'll find that to be somewhat challenging. And in fact, scientists have tried to do this for many decades now with mediocre success. In other words, the point is that 3 laws of robotics aren't exactly the answer, they're more the inspiration of what we're trying to achieve. And of course, Isaac Asimov himself played with this phenomenon in his beautiful short stories, where he was exploring how exactly these 3 laws of robotics, which sound completely reasonable, are to be interpreted. And if things are left open for depends on how it's interpreted, that's not a very good fit for the rigor of logic, and it's certainly not a very good fit for what you would like your CPS safety argument to be like. The answer, you know what, that depends, and depends on what you meant by safe, is not going to be making people very happy who are supposed to use the CPSs. So we need a more precise and rigorous story. And that's where actually I think it's easier to go back to the hybrid systems example of the bouncing ball. What does Quantum the bouncing ball want? Well, he certainly doesn't want to fall through the cracks in the ground. And we can write that down by writing down a post condition that says this hybrid program for the bouncing ball ensures that the bouncing ball's position is above ground all the time. That would be a good thing. Falling through the cracks of the ground is scary. But even if Quantum likes to bounce, he's also an acrophobic bouncing ball. He's afraid of heights. He would never like to go above the initial height. So he's got a second post condition ensuring that his position will always remain below the initial height, capital H. That's good. Only did we forget something? Yes, we did. Because even if I pointed at capital H and called it the initial height, nothing in my math here says that it is. So indeed, we also need to require something in the beginning, namely we need to require that in the beginning the value of the height variable x is exactly the initial height variable capital H, so that down here in the insurance clause it's even meaningful to talk about it. Isn't that true? And indeed, if we start at H, where we stay above ground and below H? Well, no, it's not, because even if you start at H, that could have been below ground. And as far as I know, if you start below ground, you don't always stay above ground. So we also need to require that the bouncing ball starts at a height above ground. Now these preconditions are expectations on when the CPS, or in this case, bouncing ball, is allowed to be let go. And these post-conditions describe what it guarantees. You may have also seen in programs the use of loop invariants as yet another kind of contracts where non-deterministic loops are only kinds of loops here. So an invariant such as the position is always above ground could be attached to that. But this is the kind of thing that we'll get back to in our reasoning. So for now, let's just worry about preconditions and postconditions. At this point, let's turn the informal contracts about which you should wonder when exactly they're supposed to hold true over into the precise regime of logic. by developing logical formulas for hybrid programs. And here's why. Cyber-physical systems contracts are very crucial for the safety of cyber-physical systems and should be part of every CPS design right from the get-go. Because if you think of safety as an afterthought too late, then you've already reached all the wrong design decisions. That's just a recipe for disaster. Just do safe from the get-go. In particular, contract should be part of the design. And that means we need to understand CPS programs, CPS contracts, and also how we can convince ourselves that a CPS program actually respects this contract. And that's where contracts are hopelessly at a disadvantage compared to full logic. Because logic is for specification and for reasoning. On the one hand, it's good for specifying a whole CPS program, just like contracts. But on the other hand, it's also useful for an analytic inspection of its parts. And in particular, it's useful for argumentative relations between contracts and program parts to say, yes, this CPS program actually meets its contract, and here's the reason why. I give you proof. Let's develop that. In our running example of the hybrid systems bouncing ball, quantum, let's worry how we render the preconditions in logic. Well, that should be easy. They're almost logical formulas already. For example, we could take them both together and form the logical formula x equals h and 0 is less or equal h, which is a perfectly legitimate formula for the logic. What do we do then to render the postcondition in logic? Similarly, we could take the postconditions, squeeze them together into a single logical formula, 0 less or equal x and x is less or equal h, which is the perfectly legitimate first logic formula. But how exactly are we supposed to say this logical formula is supposed to be true always after running the hybrid program? Sure, the precondition is what we expect in the beginning when we let go of the bouncing ball, but the postcondition is supposed to be true all the time. And what exactly does that mean? How do you say that in first logic? Point is, you can't really. Here's why. Well, first logic, its notion of semantics is that a formula, such as this part of the postcondition here, is true or false in a given state. That's what it's very good at. But it's a static logic. It doesn't talk about the dynamics and behavior of something. It doesn't let us talk about this formula now being true after all runs of the hybrid program. Always. Yeah, that sounds like a logician's thing. Let's introduce the always modality, the box modality, that now says that this formula x less or equal h isn't just true right now, it's true all the time. X less or equal h, x less or equal h, x less or equal h. But if you know me, you'll find out that, of course, we'll now insist on becoming more precise about what we mean by always. We mean always at all times, when what behavior happens, do we mean in all states? So let's take the always modality, become proper logicians, and parameterize it by the bouncing ball to say all of the bouncing ball's behavior such that the bouncing ball's position that it then has is less or equal h, which means in all the states we could possibly ever go to by having the bouncing ball bounce and fly, is it indeed true that x is less or equal h in each of those states? That's good. Of course, we should become more precise about the exact model for the bouncing ball. I can't pick up a physical copy of a bouncing ball and squeeze that inside a logical formula. That won't mean anything. So, but we've got the model right here already, so we can say for a hybrid program alpha, namely this one, for example, that all of alpha's behavior is such that x is less or equal h is true, which means in a state, this logical formula is true if in all the states we can reach by running the hybrid program alpha, will the postcondition x less or equal h be true in each and every one of them. Remember, how many final states do hybrid programs usually have when you start them in one state? Many, 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 because the differential equation can be followed for any arbitrary continuous amount of time usually, and that gives us here actually an uncountably infinite array of states that we have to be safe in. But that's good because we would like our CPS to be very safe under many circumstances. The logic that we've now developed by intuition is what I call differential dynamic logic. It's a dynamic logic because it worries about the dynamics, the behavior of, well, dynamical systems. See how well that fits. But the differential says that the defining characteristics of the hybrid programs inside the dynamic logic modalities is the occurrence of the prime operator in the differential equations, because of course that's what we have to worry about in order to properly understand hybrid systems. So let's use this language right away by remembering that this is the hybrid program for the bouncing ball, copying it inside the always box modality, and rendering this pose condition in it to say that all of this hybrid program's behavior is such that we're below the initial height. That translates this pose condition. What do we do with the other one? Yeah, same thing. In a similar way, we can say all of the exact same hybrid program's behavior such that the other pose condition always holds true afterwards. We could have chosen that one, right? How? Could have said always under the exact same hybrid program is the conjunction of the two true. Which of the three logical formulas is it now? Well, I don't know, but what you can certainly say is that the last one is equivalent to the conjunction of the first two, because if you always make sure you're above ground and you always make sure that you're below initial height, that's exactly the same as making sure that you're always both above ground and below initial height. So in other words, in differential dynamic logic, can you say that this conjunction of logical formulas is another logical formula in DL, and so is the by implication of the two? And indeed, the entire logical formula is a valid formula. It's true in all the states, and that reasoning wasn't even specific to this particular bouncing ball model. It holds for any hybrid program, which is an indication in early one why differential dynamic logic is also useful for reasoning about these logical formulas. But we're getting ahead of ourselves. Let's just go back to this pose condition and worry what we need to do with the preconditions. It's not actually true that we're always above ground, is it? Well, hold on a minute. I guess actually it is, because if you look at it, see, the evolution domain constraint says we're always above ground, so I guess, of course, we're always above ground without any extra assumptions, are we? No, that's not right, because if you start below the ground, then sure thing, you cannot actually solve this differential equation with this evolution domain constraint for any amount of time, not even 0, which means there are no successful runs of this program, except there still are successful runs of the repetition, and the only one, the one that says, I stop right away, because that's permitted for repetitions, and if you stop right away, I'll let you in a little secret, if you start below ground and stop right away, you won't be above ground as far as I know. That means the preconditions that we needed are really crucial, actually. So we can render them in logic 2 by assumptions, implications. Logic is very good with managing assumptions. For example, to say, if we assume x equals h in the beginning, then all of the behavior of the hybrid program is such that we're above ground, but that formula isn't quite valid yet. If we render the second precondition in logic as well, then we assume the conjunction of being above ground and at initial height h. And then indeed it is true that all the behavior of the hybrid program will be such that we're above ground all the time. Of course, it's even better if we don't just informally justify why we believe in the validity of this logical formula, but we actually ultimately are able to prove them. Good. After this motivating examples, we can properly introduce the most fundamental concept of the entire textbook, differential dynamic logic, which is the logic of the behavior of hybrid systems, which we use both for specification and also for reasoning purposes for cyber-physical systems. First, the syntax. The syntax of differential dynamic logic defines the formulas by the following grammar. The formulas P and Q can be real arithmetic comparisons of terms, logical not, and or implication, and of course all the other operators of forced logic as well. In particular, we will retain the capabilities of universally quantifying of variables to say formula P is true for all real values of x, and existentially quantifying them to say that formula P is true for some value of x. This is really first order logic of real arithmetic, except now the formulas P and Q are going to be any arbitrary differential dynamic logic formulas. In particular, The two most important additions are the defining characteristics also for differential dynamic logic. For a hybrid program alpha and a differential dynamic logic formula P, built recursively out of these operators, alpha box P and alpha diamond P are new logical formulas where alpha box P says that all behavior of the hybrid program alpha is such that the final states we reach satisfy the differential dynamic logic formula P, whereas alpha diamond P means that there is a run of the hybrid program alpha to a state where P holds true. Well, that's a syntax of differential dynamic logic, but real logicians. So, next thing we're going to do is properly define the semantics of it. And the semantics of a term was a function that maps a state to a real number. The semantics of a hybrid program was the reachability relation between initial and final states that it induces. But the proper semantics for differential dynamic logic formulas. We're still, just like in first order logic, interested in understanding the set of states in which they happen to be true, even if some of the operators, most importantly the modalities box and diamond, actually will have to refer to the reachability relation behavior of the hybrid programs alpha. Let's take that one step at a time. The intuition is going to be that in a state omega, the formula alpha box P is true, if indeed in every state that we can go to by running the hybrid program alpha, the formula P will be true in the final states of all those runs. Mind you, these are often uncountably infinitely many, coming from the non-deterministic real number duration that we follow a differential equation. The dual is that alpha diamond P is true in the state omega if there is at least one final state that we get to after running the hybrid program alpha, such that in the resulting state the logical formula P is true. Alpha diamond P is only true if there is a successor state, such that in the final state P is true. Alpha box P would also be true in the state where we cannot at all successfully run the hybrid program into any direction. Think of this like quantifying vacuously over empty sets. For example, all prime numbers that are divisible by 4 are less than 17. Of course they are, because there are just no prime numbers that are divisible by 4. That's the entire point. So it's a true, but vacuously true statement. In the same way, would it mean all behavior of a hybrid program is such that in the final states 1 is equal 42 in cases where there simply are no final states, because every which way the hybrid program is turning to try to execute, they all fail their tests all the time. So think of it like the hybrid program is desperately trying to execute, but every time it's doing that, it fails one of the test conditions and then says, I was never here, you've never seen me. The execution is undone. It didn't happen in the real world, which means there is no final state to speak of in that case. But the alpha box formula would be true if there are no final states at all. The alpha diamond formula would not be. It would require P to be true in one of the final states. It's okay if P is true in multiple of the final states. It's also okay if not P is true, so P is false in some of the final states. But P has got to be true in at least one of them. Notice that this was the transition behavior of the alpha hybrid program. In the exact same state, could we talk about the beta behavior of an entirely different hybrid program, beta, and talk about, for example, is there a beta run such that something is true? We can also nest the operators and say, is there a beta run to a state from which all the alpha behavior will take us into states where P is true? Or we can nest this with quantifiers and propositional connectives to say things like, first of all alpha behavior satisfies P, and then there is a behavior of beta such that all the alpha behavior also satisfies Q, or also satisfies that there is a value of this particular parameter such that some behavior further implies something. In other words, differential dynamic logic is a proper logic. It's closed under all of its logical connectives. Every combination of the formulas is again a formula, and we will exploit that a lot in our reasoning. Having said that, that's also very useful for specification purposes, but indeed the most canonical initial shape of formulas you will find is this one, which is like a Hoare triplet but for hybrid systems, where the initial condition is prescribed by A, which implies that all behavior of the hybrid program alpha satisfy the postcondition B. This is the precondition, and these are the postconditions of the program. But we're still in search for a proper mathematical definition of the semantics, not just pictures. So here we go. Notice for first-order logic, for reasons of simplicity, we used to define in a given state omega that a logical formula is true. For example, the formula E is greater or equal E tilde, if and only if, when we evaluate in the state omega the left-hand side term, and we evaluate in the same state omega the right-hand side term, then on the left-hand side do we get a greater or equal real number vec. That is a definition of the truth of logical formulas per state. We could also do that for differential limiting logic, but it turns out it's a bit more elegant and concise if we simply define them all at the same time. So what we will be doing here is to find the semantics bracket that defines for every differential limiting logic formula the set of states in which it happens to be true, all in one sweep. For example, the meaning of E greater or equal E tilde is the set of all states in which this formula happens to be true, which is the set of all states omega, such that when evaluating the left-hand side term in the state omega, we get a value that's greater or equal than what we get by evaluating the right-hand side term in the same state omega. We gather all of those states up and throw them inside this set. Likewise, for the not operator, the meaning of not P is that it's true in this set of states, which is defined as the complement of the set of states in which P is true, which is just all the states, and we delete out the states in which P is true. The set of all states where P and Q is true is the set of all states where P is true intersected with the set of all states where Q is true, because these are precisely the ones in which both P and Q is true. P or Q is true in the set of all states where P is true union in the set of all states where Q is true, because in these sets of states is P true and those is Q true. If we union them together, we find all of the states in which either of them is true, even the one in which both of them are true, which is perfectly legitimate of an OR operation. P implies Q is true in the set of states where the assumption is false, so the complement of the set of states where P is true, union the ones where Q is true. These are all just like in first-order logic, using your slightly differing notation. The new cases are the modality cases. The meaning of the alpha diamond P modality is that it's true in the set of states that is the relation induced by the hybrid program, a relation composed with the unary relation corresponding to the set of all states where P is true. So follow alpha to a state where P is true, but it's probably easier to define this explicitly as the set of all states omega, such that for some new state nu that you can get to from the old state omega by running the hybrid program alpha, and one of those states nu is the postcondition P true. And dually, the meaning of alpha box P is that it's true in the set of states that's either defined like this or defined explicitly as the set of all states omega, such that all the successor states nu that we can go to the new state nu from the old state omega by running the hybrid program alpha, and then all of these new states nu is the postcondition true, just like in the pictures. Alpha diamond is existential quantification over the new states nu, and alpha box is universal quantification of the new states nu. Indeed, in this new style, the meaning of exists xp is that it's true in the set of states that consists of the set of all states omega, such that for some real number r, if I change the value of the variable x to r in this state, we are in a state in which the postcondition P is true. And likewise, for all xp is true in the set of all states omega, such that for all real numbers that we could possibly ever think of, if we change the value of the variable x to be r, then in this new state is the postcondition P true. So just like exists and for all quantify over some real number or all real numbers. Do diamond and box quantify over some new state or all new state. Notice here we used the set of all states as the notation we actually define inductively, one for each case. And of course from that we can read off when the formula P is true in the state omega, just when that state is part of the set of all states in which is true, which we used to write like that in the beginning. And of course, for first order logic, we have done it the other way around. We defined this as the elementary notion and defined the set of all states out of that. But both representations are really equivalent except for style. This particular style turns out to help us a lot when doing proofs about differential dynamical logic because it makes matters easier. But just like we will still occasionally use this notation for a given state omega and a differential dynamical logic formula P to say that the formula P is true in the state omega, we will also still continue to use this notation to say that the formula P is valid because the state doesn't matter. It's true in every state, which in our new notation can also be written down as the set of all states in which P happens to be true equals the set of all the states that ever exist. Some examples. The differential dynamical logic formula, there is a D such that if we reset the variable x to 1 discretely and then follow the differential equation x prime equals this number D for some arbitrary period of time, then it all the time is the value of x greater equals 0 at the end. Is this formula true? Wait, that's not a good question. I should say, is it true in a particular given state? It does become a good question if I say, is it a valid formula? Because then I'm asking, is this formula true in every possible state you could ever think of? And yes, it is. This is a valid formula because indeed, no matter what values we've got, if we choose a clever value for D, such as 42, we reset x to 1 and then follow x prime equals 42 for any arbitrary amount of time, we will receive a value that's greater or equal to 0. The next formula discretely increases x by 1 and then follows the differential equation x prime equals d and conjectures that it's always the case that x is greater or equal to 0 afterwards. Is that formula true? And that doesn't make sense. Is the formula valid, so true in all the states? Yes, it is not. Because if we start in a state where x already has a very negative value, then if we would follow the differential equation, no matter what value d actually has for 0 amounts of time, we're below 0 at that moment, having violated the postcondition. This differential dynamical logic formula now says that there is a way of running the differential equation x prime equals d for some amount of time so that afterwards x is greater or equal to 0. Is that formula valid, so true in all states? That's more subtle, right? So if d has a positive value, say 5, and the formula is true because even if x has a negative number value initially, if we just follow x prime equals d, so in this case 5, for long enough, eventually x will have a positive value. That's good. If x initially starts non-negative, then even if d has a negative value, say minus 42, it's possible to follow this differential equation for some amount of time, say 0 time units, to go to a state where x still has a non-negative value. But the other states are the problem. The states where initial value of x is already negative, but the value of the slope d is also negative because then it just keeps on getting worse. In other words, this formula is not actually valid. The first one was valid, but these two were not. True in some states, but not in all of the states. In the long term, we will be most excited about formulas that are true in all the states because that means no matter what particular state our cyberphysical system is in, we can rely on this formula being true. Now something less interesting, admittedly. It's notational conventions for precedence operators. Why do we need them? because I would like to spare you the details of having to write down too many parentheses, because it gets hard to read formulas then, but I still want you to be able to read them correctly. We are using the same precedence conventions that we used before, which are tuned to make sure there's not that much you have to remember. All the unary operators find stronger than binary operators, but the unary ones now are repetition star, logical not, quantifiers, which only expect one formula argument, and alpha box and alpha diamonds modalities, which at least only expect one formula argument. As usual, and binds stronger than or, which binds stronger than implication by implication operators. Maybe the most subtle one. Semicolon binds stronger than non-deterministic choice. But that also makes sense, because if you think of the resemblance to regular expression, nobody in his right mind would read a regular expression like this one, where in regular expressions you leave out the semicolon and you write the choice as just a bar or pipe operator, but you would never read them implicitly like so, without explicit parentheses. So we use the same notational convention here in hybrid programs. And all the arithmetic operators associate to the left, all the logic and program operators associate to the right. Specifically, that for example means that alpha box P and Q means all alpha behavior satisfies P and Q. In particular, variable occurrences within Q refer to the initial state, but variable occurrences within P refer to the state we get to after running alpha. Just like for all x, P, and Q implicitly means for all x, P, and also Q. Variable occurrences of x and Q refer to the initial value x had before the universal quantifier. Likewise for implications. And alpha semicolon P choice gamma implicitly means first run alpha, then run beta, or make a non-deterministic choice to instead run gamma. Likewise, alpha choice beta semicolon gamma is a non-deterministic choice between either running alpha or instead first running beta then gamma. And alpha semicolon beta star implicitly means alpha followed by any number of repetitions of beta. P implies Q implies R is read as P implies Q implies R, and we expect explicit parentheses to disambiguate implication and by implication operators meeting each other, because otherwise it's really hard to decipher these formulas. Good. Now that we have a precise language of differential dynamic logic for describing hybrid systems and the expectations we have for them rigorously, let's use some lessons from the hybrid systems example of the bouncing ball to learn how to properly identify requirements of cyberphysical systems. Here's a bouncing ball model, the hybrid program for quantum, the acrophobic bouncing ball, and here's specification that always, when we start at the initial height h, at a position greater or equal 0, then all behavior of the hybrid program for the bouncing ball is such that we indeed stay above ground and below initial height. I've been cheating with notation a little bit. Really, I should have said 0 less or equal x and x less or equal h. And here I should have said h equals x and x greater or equal 0, but I was just trying to save some space on the slides. My apologies. If you do that, please don't let it confuse yourself. Now, that's the beautiful logical formula. And we have now a precise semantics for formulas, so we can ask, is it valid? Meaning, is it true in all states? Surprise, surprise. Now that we have a precise semantics of it, we find that it is not actually a valid formula. There's counterexamples. Can you think of one? If the gravity is negative, we're in an anti-gravity field, and indeed, if you try out your bouncing ball in the next anti-gravity field you will see it disappears into space. It certainly will go way above initial height, which is terrifying for acrophobic bouncing balls. It's also not a whole lot of fun bouncing there. We forgot something. Now we could say, to patch this, assume that gravity equals 9.81. But that's actually overly specific. Besides, it's wrong. Gravity constant is 9.8067, and not even quite that either. You get the point. If you're being overly precise about the parameter assumptions you have, then your theorem might stop applying to reality, plus you might actually have a harder time than necessary to prove it. Besides, next time you try your bouncing ball out in Moon, you'll find the gravity constant is 1.6, and then Jupiter is 25.9. So none of this would actually work so well. So the right thing to do is to simply assume what we need, that the gravity constant is a positive constant. Okay, now we're good to go. Now we have a valid formula, right? Wrong. We had a parameter g in the formula, forgot an assumption about it. Now we made that assumption up. But c is still the parameter. That could have gone wrong, right? Can you think of an example? Yes. If c is positive and bigger than 1, then it will be anti-damping. It will fall down, be actively pushed back from the ground, jump up faster than it used to, and in particular higher, and jump up faster and higher, and jump up faster and higher, and jump. Possibly a lot of fun, but dangerous for acrophobic bouncing balls. So we need to assume that our damping factor is an actual damping factor, which means we need to assume its value is between 0 and 1. Well, in reality, it will never actually be really 1. That would only happen in an ideal world frictionless dynamics. But, well, why bother? If we can prove our theorem safe, even some more liberal assumptions, let's do that in any case, because it's more valuable for us. Now the formula is valid because we've got assumptions for all the parameters now. Well, state variables, what about these? We have an assumption about position, that's good. We don't have an assumption about velocity. Maybe that doesn't matter because with velocity it doesn't even play a role in the postcondition. But let that be a lesson to you. That's not right, because the way the position that we care about changes depends on velocity, so we indirectly are interested in velocity and have no assumptions about it. Could that possibly ever go wrong? Yes, it could. Because if the initial value of the velocity would be positive, we would throw the ball upwards in the beginning, and, well, guess what? It'll climb and be higher than the initial height. Even if it ultimately is fine again, we have already violated the safety of the system at this point, for example, and that's bad. So we have to make sure the initial velocity is less or equal 0. Now we've got assumptions for all the parameters, so what could possibly go wrong? Still one very subtle mistake. And the problem is that your initial velocity could be negative, but very negative, all right, like so, which means you're initially strongly pushing the bouncing ball downwards, just like a dribbling basketball, which will come back up higher than it originally was. And even if the bouncing will ultimately be below ground, we have still already violated the safety of the system here, there, and there, for example. So the formula is not a valid formula unless we fix those assumptions. I invite you to think about what the exact assumptions on the initial velocity are. To make our lives easy, we'll just say you let go of the bouncing ball without giving it any initial upwards or downwards velocity. Initial velocity is 0. Now, indeed, through scrutinizing every assumption in the system, we have made sure we ultimately have a formula that deserves a proof because it's actually a valid formula. And in general, this is a good idea. Before you go ahead and prove something, see if you can find mistakes for yourself, because they might save you a lot of time in going down dead ends in the proof search. Another example is the robot that's moving on circular arcs and lines and circular arcs and circular arcs and lines, where we've seen the model of a repetition of a differential equation where we first set the angular velocity to be -1 or 1 or 0, depending on whether we want to move a left curve or a right curve or a straight curve. And, for example, the specification for it would be that we never want to reach an obstacle position O. But of course, we have to make sure that we at least didn't start in a colliding state, and then all behavior of the robot moving around such that the position is not the obstacle's position. Is that now a valid formula? That has an unambiguous, precise answer. It turns out if you do this incorrectly, then you will hit the obstacles. You can't twist and turn arbitrarily, but there are conditions that you need to meet before you choose any of the control actions. If you set them properly, you'll have a sporting chance to get your robot correct. Let's summarize what we've learned in this important integral lecture on differential dynamic logic. We've seen the entire language that we'll need in this textbook. Differential dynamic logic as the language for talking about the behavior and proving properties of the behavior of hybrid systems, where the language comes with two syntactic categories on top of terms. The hybrid programs category for describing the behavior of the system, and the differential dynamic logic formula category for describing expectations about the behavior of the system. What it brings is assignments as atomic operations for discrete dynamics, tests for logical formulas as the atomic operation for imposing conditions on the execution of the system. Most importantly, the defining characteristic of differential equations with evolution domain constraints in the program as the atomic operations for continuous dynamics, and then these are combined with programming language principles such as the non-deterministic choice operator between alpha and beta, choose whether you fly upwards or whether you fly downwards, for example, sequential composition operation, first fly upwards and then fly downwards again because you want to land, and non-deterministic repetition, let your flight control loop take a number of iterations until you're safely at your target destination. Indeed, with these operations of hybrid programs that are the elementary ones, you can define all other operations of programs as well. Differential dynamic logic formulas start with arithmetic comparisons of the arithmetic term e is greater or equal e tilde, for example, but also other ones like less than and equality and so on, because they're definable out of this and the other primitives I'm listing here. Logical negation, conjunction, out of which of course you get all the other propositional connectives such as or and implication and so on. Please don't write them down literally like this in your examples, but in theory it's always nice to have a small set of primitives to worry about, while in practice it's useful to have a few more derived ones as well. And the quantifiers are first of the logic of the reals for all x is p true or there is an x such as p true, both of those quantify over the set of all real numbers. Useful, for example, to talk about all positions or some velocity satisfy something. And most importantly, the modalities that connect the hybrid programs with the differential dynamic logic formulas. Because for every hybrid program alpha built recursively like so, and for every differential dynamic logic formula p built recursively like so, is alpha box p and also alpha diamond p a new logical formula, where alpha box p says that all runs of the hybrid program alpha are such that the final states we get to satisfy the DL formula p, while alpha diamond p says that there is a way of running the hybrid program alpha to a state where p holds true. The semantics is the following, where the semantics for a hybrid program is a reachability relation relating initial states to some final states, and the semantics of differential dynamic logic formulas is a function that maps formulas to the set of all states in which they happen to be true. For assignment, the semantics is a relation that's actually a deterministic relation, because for every initial state omega there's exactly one new state nu, the one that agrees on all the variables with the old state omega except the value of the variable x that's changing, whose value is supposed to be the value of the right hand side in the initial state omega. The behavior of tests is that for every state omega there's at most one successor. If there is a successor, it's this test itself, it doesn't change state, but that successor is only available if in that state is the logical formula q even true. For differential equations now, there's a lot of behavior usually, because it's the set of all pairs from the state at the initial time 0 to the state at the final time r for any duration r of a solution phi that solves the differential equation x prime equals f of x at every moment in time between 0 and r. For non-deterministic choices, the behavior of a non-deterministic choice is the union of the behaviors of the left-hand side program and the behaviors of the right-hand side program. Sure, a choice has a choice between being like alpha or being like beta. The meaning of alpha semicolon beta is the relation composition of first running alpha through some intermediate state and then running beta. And the meaning of non-deterministic repetition of alpha is the reflexive transitive closure of the relation induced by alpha, or an arbitrary n-fold iteration of the program alpha, alpha semicolon alpha n times. Observe how this was a compositional semantics. The meaning of something is always a simple function of the meaning of the pieces. And the same in differential logic formulas. The meaning of e greater or equal e tilde is the set of all states in which evaluating the left-hand side gives us a value that's greater or equal than evaluating the right-hand side. The meaning of not p is the complement of the set of all states where p is true. The meaning of p and q is the set of all states where p is true intersected with the set of all states where q is true. The meaning of alpha diamond p is the relation composed of the transition relation of alpha followed by the set of all states where p is true. That means follow alpha to any state where p is true, which means it's true in the set of all states omega, from which you can go to one new state nu by running the hybrid program alpha, such that in at least one of these new states nu is the postcondition p true. And dually, alpha box p is true in the set of all states that is like so, or that is the set of all states omega, such that all of the new states nu that you can get to by running from the old state omega, the hybrid program alpha, is the formula p true in this particular new state nu for all of them. And for example, the meaning of the existential quantifier is that exists xp is true in the set of all states omega, such that for some change in real value of the variable x is in this new state, the logical formula p true. The semantics of all of the hybrid program operators and all the differential logic formula operators were perfectly compositional as a simple function of the meaning of the pieces, which we will exploit next time to make sure that our understanding and analysis and proofs of them also everything will be a simple function of the individual analysis results about the pieces. And that is how even very complicated cyberphysical systems can be mastered and understood well.